Hello everybody, so welcome to this e-lesson on the uniqueness principle. So let's begin. Now, all elements in the periodic table are arranged in according to periods, which are the horizontal rows, as well as into groups, all right, which are their vertical columns. So for this lesson, we're going to be focusing on period 2 elements, which exhibit actually quite unique properties from their counterparts within the corresponding groups. So let's take a look at a few examples first. So for example, you were taught in lower years that group 1 salts generally are very soluble in water. Now, however, lithium salts are actually less soluble than their sodium and potassium counterparts. In fact, lithium salts are more soluble in the less polar alcohols than their sodium and potassium counterparts. Okay, another example that we can see is for beryllium. For beryllium compounds generally are covalent, such as beryllium chloride, right, BeCl2. If you recall how to draw the Lewis structure of beryllium chloride, it's like this, BeCl, Cl. All right. Now, the fact that we draw a single line between the chlorine and the beryllium, right, this indicates that it's a covalent molecule. Now, however, if you look at the other counterparts within group 2, right, such as magnesium, calcium, and barium, now those are ionic compounds, all right, such as this CaCl2. This is an ionic compound. So other examples include like oxygen. Oxygen forms p-pi bonds, all right, and exists as O2. Now, however, sulfur doesn't. Sulfur does not form S2. Okay, sulfur does not form S2. Instead, it forms S8. Now, S8 has this kind of structure, all right, where every corner is a sulfur atom. So as you can see within this structure, S8 is actually a crown that is held together by single bonds. Right? There are no double bonds present in sulfur. Okay, so this is how it is. Oxygen is unique from cases like sulfur and some other elements within group 16. Now, so why is this the case? Why are period 2 elements so special? So there are actually 3 reasons that are able to explain the unique properties of period 2 elements. Now, firstly, period 2 elements have an exceptionally small size. Okay, they have an exceptionally small size. Now, secondly, they have an enhanced ability to form pi bonds. Now, in this case, the type of pi bonds that they are forming are generally 2p pi bonds, and we will see why this is important later on in this lesson. And lastly, the last reason that can explain their unique properties are their unavailability of the d orbitals in these elements. When we say unavailability, what we are saying is that they are energetically inaccessible. All right, the d orbitals of, say, lithium are energetically inaccessible. So let's take a look at an example. Now, if we look at lithium chloride, we would expect it to be an ionic compound, right? Because it's Li plus and Cl minus. Okay, similarly, for Be and Cl, okay, because we expect this to be a cation and these to be, sorry, the negative sign missing here, these are to be anions, we expect them to be ionic in nature. However, if we were to look at the analysis of these 3 compounds, we actually find some deviations from the ionic properties that we would expect. For example, for lithium chloride actually shows some covalent character in its bonding. Now, lithium chloride is still effectively an ionic compound, okay, but within the bonding, we actually see some covalent character in its bonding, and I will explain what this means later on in the next slide. For beryllium chloride, we saw in the previous slide where we drew the Lewis structure that is actually a linear covalent molecule. So this is not that it has only covalent character. This is a totally covalent molecule. Similarly for BF3, boron trifluoride, we see that it's a trigonal planar covalent molecule. Now, although in this molecule, BF3, we use fluorine, which is a super electronegative atom. Okay, we would expect fluorine compounds to actually be ionic when it's bonded to a metal, but in the case of BF3, it actually exists as a fully covalent molecule. Okay, and we're going to see how this is possible in a short while. Now, generally, compounds will have high covalent character in their ionic bonds. Okay, if the cation has a very high charge and a small size, and if the anion has a large size. So why is this important? So let's take a look. For example, in the case of lithium chloride, the lithium cation actually has a very high charge density. What does charge density mean? The charge over size ratio. Okay, so in the case of Li+, it has a very high charge density, and this makes it highly polarizing. Now, the anion that it's bonded to has a large electron cloud, and this makes it very polarizable. Now, please make the distinction between these two terms. This was covered in year 3 when you did intermolecular forces, so hopefully you still remember how these two terms are used. Polarizing refers to the ability of the cation to distort the electron cloud. Polarizable refers to how easily the electron cloud is distorted. So let's take a look at a visual representation of these two terms. Now, the cation is polarizing, meaning that it has an ability to distort the shape of the chloride's electron cloud. The chloride is polarizable because it has a large electron cloud that can be that can have its shape distorted pretty easily. So as a result, because of the high polarizing power of the lithium plus, it sucks some of the electron density from the chloride over to its side. All right, the lithium actually sucks some of the electron density over to its side, and this distorts the electron cloud from the typical spherical shape that we would expect. Okay, so and this would be the representation of the electron cloud density in lithium chloride. Is it still an ionic compound? For the case of lithium chloride, yes, but we see some covalent character. What does this mean? If you see this portion here, there is some electron cloud density that lies between the lithium and the chloride, which is typical of a covalent bond, right? Which is shared between the two nuclei. So this is what we mean by covalent character. So the higher the charge density, the greater the polarizing power of the cation. Okay, so as we can see in sodium, if you compare sodium, magnesium, and aluminum, their ions, okay, have increasing charges, right? But the ionic radius of these three ions decreases across the period. Therefore, it results in a higher charge density as we go across the period. So because of the increasing polarizing power of these three ions, we see that the distortion of the oxide anion actually increases. All right, and in this case, we see that in the case of aluminum oxide, the oxide's electron cloud is distorted to the greatest extent. All right. So how can we apply this? We can apply this to our understanding of thermal decomposition. Now, if you look at this equation is an equation covered in lower year chemistry, where under high heat, usually a group 2 carbonate will break down. All right, it will break down via a process known as thermal decomposition, and it will form a group 2 oxide and carbon dioxide in the process. So, looking at this diagram, now please take note, this sign here is not an equal sign. this is the way this diagram is showing the double negative charge on the carbonate anion. Okay, CO3, 2 minus, right? So this is how this particular diagram is showing the double negative charge. Please don't show it this way when you draw. Okay, it should be single negative charge on one O, single negative charge on another O, and the double bond to the last O, like in this case. Again, drawing the lone pairs yourself, but this is the way the negative charges should be distributed. Okay, now, so if we look at this diagram, now we said that the cation has a high polarizing power, and because of its high polarizing power, it sucks electron density over to itself from the anion. Now, if we look at this anion, all right, if we look at this anion, we can see that electron density is actually sucked towards the cation, right? And it is this particular bond that has its electron density sucked over to the cation. Now, when electron density is sucked over to the cation, the electron density between the O and the C decreases. And as a result, this weakens this CO bond. Now, when this bond is weakened, all right, when I subject this compound to high heat, okay, when I subject this compound to high heat, this bond, because the electron density, some of it is sucked over to the cation, it breaks easily. As a result, this portion will become carbon dioxide. This portion will become the group 2 metal oxide. So what is the temperature required to break this bond? It depends on the cation. So down a group, okay, as we go down group 2, the M2 plus cation becomes larger and larger. Now, because of this, the charge density decreases and its polarizing power becomes weaker. So as a result, the carbonate becomes more and more stable. It requires more energy to force the group 2 carbonate to undergo thermal decomposition. So if we compare the decomposition temperature of, say, magnesium carbonate and compare it to barium carbonate, okay, magnesium carbonate will have a lower decomposition temperature, okay, because it is the Mg2 plus is more polarizing than the Ba2 plus. Less energy is required to break this bond to release the CO2. Now, another property that period 2 elements have, okay, that makes it exhibit unique properties, is their enhanced ability to form pi bonds. So let's take a look at O2 and S8. Now, let's think about this. Instead of S8, why can't sulfur form S2 then? Now, in O2, in the case of O2, O2 uses 2p orbitals, right? O2 uses 2p orbitals to form the pi bond. So essentially, they look like this. Let me try to correct that. Okay, so one 2p orbital, the second 2p orbital. But if I want to form S2, it needs to use the 3p orbitals to form a 3p pi bond. Now, if this were to be the case, okay, if this would be the case, what we would see would be this. Okay, because the only difference between the 2p and the 3p orbitals in terms of the physical properties is the size. Okay, so this is the O2 pi bond, and this is the theoretical S2 pi bond. Now, in the case of S2, this area and this area, we are comparing the overlap, this area versus here and here. Now, if you just compare the size of the overlap, okay, if you just compare the size of the overlap, this overlap in the 3p orbitals appears at face value to be larger than the 2p overlap, right? So shouldn't this bond be a stronger bond? No, it shouldn't. Okay, it shouldn't. Why? Let's take a look at this. Now, in one bond, for every bond, in one bond, there are 2 electrons, right? So if 2 electrons are spread out, okay, if 2 electrons are spread out over a volume like this versus 2 electrons spreading out over a volume like this, all right? Although we see that here there is a supposedly larger overlap, we need to bear in mind, okay, that these 2 bonds each only have 2 electrons. So if 2 electrons are spread out over such a large volume, the overlap that is here actually has less electron density than the overlap in the 2p orbitals. Okay, the overlap in the 2p orbitals, the extent of effective overlap in the 2p orbitals is actually much greater and much more effective than between the 3p because the electrons in the 3p bond, pi bond, they are more spread out across the entire orbital. So the overlap here is actually very poor. Okay, and as a result, it results in poor or weak bond being formed. Okay, in the case of a 3p bond. So if we compare that and contrast that to what we see here, okay, in the 2p orbitals overlapping, okay, there is actually a much more effective overlap if I use 2p orbitals to form a pi bond. Okay, and the pi bond that is formed from 2p orbital overlap is very strong. And this results in a stable molecule being formed. So therefore, if we go back to the example on O2 and S2, okay, if we go back to the example on O2 and S2, the pi bond formed in the O2 molecule is actually much stronger than the pi bond formed between S2. Okay, because this is from a 2p overlap. This is from a 3p overlap. So as a result, this bond, right, this pi bond is much stronger than the 3p pi bond. Okay, because the overlap between these 2 orbitals is much more effective. So similarly, we can also see that, so as we just discussed, O2 and N2, they exist as this. Okay, because we have just seen, okay, with silicon and with sulfur, okay, the overlap of the 3p orbitals is much less effective. Okay, it's much less effective for the reasons just discussed. Because when I overlap a 3p, okay, the electron density here is much less than that in the 2p because the same 2 electrons are distributed over a larger region of space due to the larger 3p orbital. Okay, so the overlap here is poor. It makes for a weak bond. Therefore, S2 will be highly unstable. The same explanation can be applied to why we see CO2 molecules in this form, but we will never have SiO2 in this form. In fact, SiO2 exists as a giant molecular structure. Okay, so because in CO2, okay, the overlap between the 2p orbital of the carbon atom and the 2p orbital of the oxygen atom is very effective. And as a result, because of this very highly effective overlap, it results in a strong pi bond being formed between the carbon and the oxygen. So this makes CO2 very stable. Now, SiO2 cannot exist in this form. Okay, because the 2p, 3p overlap is weak. Okay, it is it's poor. The overlap between the 2p orbital and the 3p orbital is poor. It results in a weak pi bond. Therefore, silicon dioxide in this form with two double bonds is highly unstable. So as a result, okay, SiO2 will prefer to exist in this form. Okay, where each silicon is bonded to 4 oxygen atoms and each oxygen atom is bonded to 2 silicon atoms. Now, since we're looking at this structure, I would like you to think about this. Why do we write silicon dioxide as SiO2? Why do we not write it as Si2O4? Because if you look at this structure, the structure that my mouse is hovering over now is the structure of silicon dioxide. The purple sphere in the middle refers to the silicon. The red spheres refer to oxygen. So if we look at the purple spheres and you count the number of red spheres around them, okay, this purple sphere has 1, 2, 3, 4 oxygen, right? This purple sphere has 1, 2, 3, 4 oxygen. This one also has 1, 2, 3, 4 oxygen. Now for the oxygens, each oxygen, let's go to this one, each oxygen has 1, 2 silicon, right? This oxygen has 1, 2 silicon. So essentially, as I just said, each silicon has 1, 2, 3, 4. So why do we not write the silicon dioxide formula as Si2O4? Why not? Think about it, and we will discuss this in class. All right, moving on. Now, for the last property of the period 2 elements, the it's actually due to the unavailability of the d orbitals in these elements. Okay. Now, for example, CCl4 does not undergo hydrolysis, but SiCl4 does. Now, please be careful about this term, the unavailability of d orbitals. I said unavailability. At the beginning of this lecture, I said this means that they are energetically inaccessible. So does carbon have 3d orbitals? Yes, it does. Does hydrogen have 3d orbitals? Yes, it does. It's just that they are too energetically inaccessible because of their super high energy. Okay, if you recall, what is the definition of an orbital? An orbital is merely a region of space where there is a 90 to 95% chance of finding an electron. Okay, so does carbon have 3D, 4D, 5D orbitals? Yes, it does. It's just that they are energetically inaccessible. So, what does this have to do with CCl4 versus SiCl4? Now, if you recall, CCl4 last semester in CM5107, all right, we use this as a solvent, right? we used it as a solvent, mainly to dissolve this compound, right? Now, bromine, liquid bromine is a very reactive substance, and in order to contain it, we had to dissolve it in this, right? Because this is a highly inert solvent. But if you look at the silicon counterpart, silicon tetrachloride actually is highly reactive, especially if it touches water. CCl4, if you drop it into water, it will just form two immiscible layers. Okay, H2O and CCl4. There's nothing wrong with the diagram, okay? CCl4 is denser than water. As a rule of thumb, organic solvents that contain a halogen are denser than water, okay? So if I stir CCl4 with water, CCl4 will form, CCl4 will sink in water to form two immiscible layers. But if silicon tetrachloride touches water, okay, if silicon tetrachloride touches water, it actually undergoes a chemical reaction with water, okay? And this is known as hydrolysis. So what happens? The water will attack the silicon in silicon tetrachloride. If you recall, this is the nucleophile attacking the electrophile. So what is the process? Let's take a look. Okay, because silicon has energetically accessible vacant 3d orbitals, it actually accepts a lone pair from the attacking water molecule to form a 5-coordinate intermediate. What does this mean? This 5-coordinate intermediate actually looks like this. So silicon, right? Silicon. Now it is a 5-coordinate, meaning there are 5 single bonds bonded to the silicon. So in this case, silicon tetrachloride, after it's attacked by water, it will form this intermediate. Okay, and this is the 5-coordinate intermediate that we were talking about earlier. So this 5-membered coordinate, all right, is trigonal bipyramidal, all right, with respect to the silicon. Okay, so if you recall, okay, on the previous slide, we showed here that the water is attacking the silicon, nucleophile attacks the electrophile, and this is the intermediate that is formed. After it forms this intermediate, okay, the H will get kicked out by the O, and the silicon will kick out one of the chlorine, and this will result in HCl being formed. Okay, so this attacks it, it kicks out one of the chloride, and it kicks out HCl. Okay, and in this process, it will form silicon, the silicic acid. Okay, sorry, I think there's something missing here, Si. Okay, so this repeats until it forms SiOH4. Now this undergoes dehydration and eventually it forms silicon dioxide. Okay, now why is silicon tetrachloride able to do so? It is able to do so because if we compare CCl4 and SiCl4, now CCl4, because the carbon is much smaller than the silicon, the 4 chlorine atoms around C will crowd around the C, and this gives the molecule very large steric hindrance. So if the water molecule wants to come in to attack the carbon, it cannot do so because the 4 chlorine atoms are blocking the way. Now with silicon, this is much less of a problem. Now, although carbon and silicon are just one position away from each other in group 14, okay, the difference in the size is very large. As I've told my classes, if the hydrogen atom is a baseball, the lithium atom is the size of a stadium. Okay, so if we compare that analogy and we have that perspective in mind, okay, carbon compared to silicon, we can think about how different the size is. Okay, so as a result, there is very much less steric hindrance that the silicon experiences due to its much larger size, even though it also has 4 chlorine atoms surrounding it. Now, in addition, okay, as we mentioned just now, silicon has energetically accessible vacant 3D orbitals. So let's take a look. If I want to form silicon tetrachloride, okay, let's look at the orbital box diagram. Now, silicon has the following electron configuration, right? So neon, then we have the 3s and the 3p, right? So the 3s is filled this way, the 3p is filled this way. But silicon tetrachloride needs to form 4 single bonds. So in order to do that, it needs to promote, right? It needs to promote the electron from the s orbital into the p orbital. This then undergoes hybridization, and it forms 4 sp3 orbitals, degenerate sp3 orbitals. But in this process, the 3d orbitals were never used. But they're in the same principal quantum shell, isn't it? Right, so the sp3 does this, and after it forms the single bonds with the chlorine, it forms this. So when I stir silicon tetrachloride with water, the lone pair on the water will fit into one of the vacant, energetically accessible 3D orbital to form the 5-membered coordinate intermediate. Of course, after it forms this, eventually one of the chlorine gets kicked out to form what we saw just now. Right? To form what we saw just now here. Okay? So this is how, okay, the uniqueness principle applies. For carbon, carbon does not have energetically accessible 3D orbitals, but silicon does. Okay? Silicon does. So therefore, silicon can undergo this process, whereas CCl4 cannot do so. Right, so if we consider this property, right, we should be able to explain the next part. If we look at the next part, let's look at this question. Why can nitrogen only form NCl3, but phosphorus can form up to PCl5? Now, this is the same reason as what we just saw with the silicon versus the carbon, okay? Because in the case of phosphorus, phosphorus can use the energetically accessible 3D orbitals, but right, nitrogen cannot, because nitrogen, the electron configuration is 1s2, 2s2, 2p3. If it wants to use the d orbitals, it needs to go to the next principal quantum shell, which is too high in energy. Okay, but in the case of phosphorus, promoting from the 3s to the 3d is energetically feasible. All right, so therefore it's able to form the sp3d orbitals, the 5 sp3d orbitals, to form eventually PCl5. Okay, so with this, we have come to the end of the lesson on the uniqueness principle. If you have any further queries with regards to this section, please approach your chemistry teacher. Right, thank you.